Hello, let's go ahead and get on with a lecture, this time on expected value. So my hope here after this lecture is that you'll actually have a better understanding of when it's actually a good idea to maybe gamble or enter a lottery or things like that. You'll find that most of the time it is not ever really a good idea to do those things from a mathematical standpoint. So let's go ahead and get right into it. So this idea of expected value, I'm going to define it in a second, but what I really want to make clear is that the words itself, the term, the phrase itself, expected value, kind of tells you what it is that we're talking about. We'll see this, as I said, in the context of lotteries or gambling or things like that. And expected value, it really is. It's the value that you can expect to get out of entering this lottery or gambling or playing maybe playing roulette or something like that. So let's look at a mathematical definition of this. So basically, what we'll say is, let's say we've got an experiment, whether it be um, rolling a die, maybe flipping a coin, or entering into a lottery, and whatever you're doing, whatever this experiment, whatever this thing is that you're taking part of, there are different outcomes, right? If it's flipping a coin, your outcomes are heads or tails. If it's rolling a die, your outcomes are any number between 1 through 6. If it's entering a lottery, you could win or you could not win. And so there's multiple outcomes depending on whatever you're doing. And what I'm writing out here is, in this case of there being n outcomes, so just using a general n, because I don't know exactly what scenario we're talking about. There could be a whole lot of outcomes, there could be just a small number of outcomes. But basically what we do is we look at the first outcome, and what we do is we multiply what happens in that outcome. We multiply that by the probability of that outcome happening. And then we look at the second outcome and we multiply what happens in that outcome by the probability of that outcome happening. And then we keep doing that until we've run out of all of our possible outcomes. And so let me be very clear here with one other thing. This P with the parentheses x1, this is not a multiplication here. This in the box, well, in all of these boxes, I'll go ahead and box all of these. These are all one thing. That's function notation, not multiplication there. So it's saying the probability of x1, x2, xn. So let's go ahead and look at a very simple example here. Let's say that we're rolling a die. So roll a 6-sided die, just a standard die. So we're going to do this here. And what happens is, basically what I like to do is I like to list out the outcomes and the probability of each of those outcomes. And so when I look at this, I see, all right, I've got outcomes. Well, I could roll a 1, I could roll a 2, I could roll a 3, I could roll a 4, I could roll a 5, or I could roll a 6. And those probabilities of each of those happening, it's 1/6 every single time, as long as it's a fair die, as long as it's not loaded or weighted. So we've got our probabilities, we've got our outcomes, and now it really just is as simple as, if we're going to calculate the expected value, which I'm going to label by E, it really just is this x1 multiplied by p of x1, and we just keep doing that until, in this case, we have 6 outcomes. So I'll just go ahead and write 6 there. We add all these up, it's basically me saying, well, I can get a 1, and that happens 1/6 of the time. Or I can roll a 2, and that happens 1/6 of the time. Or I can roll a 3, and that happens 1/6 of the time. And then we just keep finishing all this out. You'll notice here this is pretty repetitive because our probabilities of each of these outcomes happening are the same every single time. And so it's a little bit boring there, but in reality, we might have different probabilities for each of these outcomes here that they correspond to. And so in this case, you actually happen to get 3.5. and that's our expected value. And now, from what we've talked about so far, we don't really have much of an intuitive understanding of what this actually means. It's like, so far, we're kind of just at, all right, we calculated this thing called E, expected value, and we got 3.5. What does that actually mean? Well, what this actually means is it's saying that if you were to roll a six-sided die, the value given by these, you can see all the different values that you could get 1 through 6. So if you were to roll a six-sided die, the value that you would expect to get is a 3.5. And this seems weird because obviously 3.5 does not occur on a die. It doesn't actually show up there. And so what's actually going on here? Well, in this idea of expected value, it's saying if you had to pick a number, if you had to pick something that you said, all right, roll a die, I'm going to pick something that I think you're going to get. You would do the best if you picked something like 3.5. Now, obviously, that's not going to happen here because you're rolling either a 1 or a 2 or a 3 or a 4 or a 5 or a 6. But this calculation, it shows you what is most likely to happen. And it's kind of like, we want to think about this in terms of an infinite sense. Let's say you kept rolling this die over and over and over, and you took an average of all of the results that happen. So let's say you roll this die 1,000,000 times, you took an average of that, you'll get 3.5. And I actually recommend you doing that. Maybe if you have a set of dice laying around, roll a die, 10, 15, 20, 30, 40 times, something like that, and average out your results, and you should see something near 3.5. So we'll see a better example of how to actually interpret this expected value here in a second when we do a lottery example. But this is basically saying that, yeah, I expect to get a 3.5 here when I roll this die, which obviously does sound weird. But let's go ahead and do another example, and we'll get an answer for our value of E, and we'll be able to interpret that a little bit more easily. So we have a prize in a raffle that's a $350 flat screen TV. And for the purposes of this problem, I don't really care that it's a TV. It's just really, let's just say you're winning $350. And so during the raffle, they're going to sell 1,000 tickets for $1 each. And what I want to know is, what is the expected value if you buy one ticket? And so really what I'm saying here is, if you buy a ticket, how much can you expect to win in this lottery? And now, obviously, if you buy one ticket, one of two things are going to happen. You're either going to win the $350 TV, or you're going to lose and basically spend that dollar. And so right there, that actually gives me a nice table for my outcomes and my probabilities. So we've got that right there. Let's go ahead and write the outcome is that I could win. And let me be clear. I could win. No, well, we'll say win and then lose. And then the probabilities of that happening are, well, there's 1,000 tickets, and if I'm buying one of them, then I have a 1 out of 1,000 chance of winning. And that means I have a 999 out of 1,000 chance of losing here. So we've listed our outcomes and our probabilities. And what we might want to ask ourselves here is, well, wait a minute, what happens in each of these outcomes, right? When we looked at this die, rolling a die example, we had our outcomes that were just the value of what was shown, right? A numerical value. So we should probably assign some numerical values to these outcomes. And we can actually do that intelligently. We can say here that I'm actually, if I win, we can actually figure out how much I'm going to win. So let's go ahead and do this. Going to sort of extend this table just a little bit. So if I win, I'm going to win $350 minus the $1 that I spent to buy a ticket. So I'm actually going to win $349 if I win. And then if I lose, I am going to lose $1 because I paid for my dollar ticket and I didn't win anything, so I just lost $1. And this assigns numerical values to these outcomes here. And those values are dollar amounts. It's telling me how much I win or how much I lose. So if we go ahead and we work this out, let's go ahead and calculate our expected value here. So E is going to be what happens in this first outcome multiplied by the probability of that outcome happening, plus what happens in the second outcome multiplied by the probability of that happening. And in this case, we're done. We don't need to add any more after that because there's only two outcomes. So remember, this first outcome was that I win $349, and the probability of that happening was 1/1,000. And then the second thing that could happen was that I could lose $1. And so be careful here. I'm going to put -$1 because I'm losing that dollar. I don't want to just put 1 because I'm not winning $1, I'm losing it. And the probability of that happening, as we saw, was 999/1,000. And so if I actually do this math, if I just do this multiplication and this subtraction, if I actually work this out, I get -65 cents. So a little shy of $1. And this is a little bit more interpretable than our rolling our die example here. What this says here is that if you play in this raffle, if you actually play in this lottery, you can expect to lose 65 cents. Now, obviously, you're not going to exactly lose 65 cents if you play this because there's only two things that can happen. The only two things that can happen are you win the TV, meaning you gain $349, or you don't win the TV and you lose your dollar on your ticket. So obviously, these are the only things that can happen in reality, but this is what you would expect to happen. And what I mean by that, expecting on what to happen, it's basically saying if you played this raffle, this lottery forever, on average, what's going to happen? And well, you could start to think about this. You could say, all right, well, let's say that we just kept playing this over and over and over. Well, on maybe here, let's just say 1, 2, 3, 4, 5. So we're playing this over and over, and then we keep playing a 347th time, we play a 348th time, 349th time, and a 350th time. Oh, I'm sorry. I'm picking wrong numbers there. Give me a second. So let's say we play a 998th time, a 999th time, and 1,000th time. So in each of these times that we play, something is going to happen. We're either going to win or we're going to lose. And obviously, most of the time we're going to lose. There's only a 1 out of 1,000 chance that we win. So really what I could probably say is that, hey, I'm going to lose, I'm going to lose, I'm going to lose. Maybe I get lucky on this fourth time though and I win. Well, probabilistically, what seems like it's going to happen here is that I'm going to win 1 out of every 1,000 times. And in this sort of simulation that I'm running, in this example, I happen to have won on the fourth time. But basically, out of this first 1,000 times, you could figure out that you're going to just keep losing over and over and over, but you're going to win one time, probabilistically, sort of on average. And so what happens when you actually do this is you're losing $1. You're losing $1. You're losing $1. You're winning 349. You're losing $1. You're losing $1. And that losing $1 just keeps happening because you're losing all these times. And so if you were to play this game 1,000 times and you added up all of your winnings and your wins and your losses, you would end up with this negative 65 cents because you're going to win every once in a while, but really every 1 in 1,000. But every other time you're going to lose $1 here. And so this calculation here, it just says if you were to play this forever, you can expect to lose 65 cents for every ticket you buy, every time you play this. So what we're seeing here is that if you play this, you're expected to lose money. So I might ask the question, should you actually play in this raffle? And the answer to that would be no, we don't want to play in this raffle because we're expected to lose. Let's say this. What if you bought all 1,000 tickets? Well, you just spent $1,000 to buy all the tickets and you won a $350 TV. So let's actually go ahead and look at this. So let's say, what if I bought every ticket? So in this scenario, I'm buying 1,000 tickets, which cost me $1,000. And then because I've bought every ticket, I'm guaranteed to win. No matter which ticket they call, I'm going to win because I have all the tickets. So my net my net amount here is going to be the $350 that I gained minus the $1,000 that I paid for all these tickets, which is $650 here. And so if I just buy every ticket, obviously that's not a good strategy here because I've lost $650 because I spent $1,000 on all my tickets, but I made $350 on winning this TV. And so I spent $650, or I basically lost $650. So if I think about this on a per ticket average, I lost $650. So per ticket, I lost my $650. Make that look a little nicer. I lost my $650 divided by the 1,000 tickets that I purchased. This actually gives me that same amount that we saw before, that negative 65 cents. So per ticket that I buy, if I were to just buy all of these tickets, per ticket, I'm losing effectively 65 cents because in total I'm losing 650 and I bought 1,000 tickets. So effectively per ticket, I'm losing 65 cents. So that tells you that you shouldn't buy a ticket because you're expected to lose 65 cents. And that's really expected value. That's the math of it. That tells you explicitly that you should not do this. And it's very easy to convince yourself, oh, well, what if I just buy one ticket? Because then I'm only losing $1 and I have the chance of winning a $350 TD. I can make a lot of money. And that's fine to think about that, but it's not mathematically correct because mathematically, if you buy that ticket, you're spending $1, but your chances of winning that $350 TV just aren't high enough to make it actually worth it because on average, you're losing 65 cents per ticket that you actually buy. And so you would not want to play this raffle. You're expected to lose. The value for each ticket that you buy is negative 65 cents. So we don't want to play. An interesting fact in roulette, actually, if you're at gambling and you're playing at roulette. So a roulette expected value calculation, we could look at this and we could say that there are 38 different options for what you can get in roulette. There's 39 options because there's 18. Let me go ahead and write all this out here because I'm just kind of rambling. So we've got in roulette, we've got 18 blue or 18 black, we've got 18 red, and then you typically have one 0 or a black. Let's say black. Or yeah, it's generally just a 0 there. And so what you notice here is that if you bet on black or you bet on red, you have an 18 out of 37 chance, actually. So I'm slightly off of my numbers there. There's 37 total here. So you'll notice that there's 18 out of a 37 chance of you winning if you bet on black or red. And really what this does is this extra little 0 roulette option that you could get, it really just shifts the balance of this expected value into the favor of the casino or whoever's actually doing this. And so it turns out that if you bet on a roulette table, it turns out that you lose about 5 cents every time you play. And obviously, if you're a casino and you're hosting this roulette table, you've got thousands of people coming in every day and playing at roulette. And if they're expected to lose 5 cents each time, in that large of a quantity and those large of numbers, it turns out that basically the casino makes 5 cents every time that roulette wheel spins. And if you look at their math and you look at how much they make on it, it actually turns out to be that. So a great example of where casinos and gambling just isn't really worth it. Roulette, I'll go ahead and write this out explicitly. In roulette, the expected value is -5 cents, roughly. And so that's just saying, hey, don't play roulette because you're expected to lose 5 cents every time. So a good example of why not to gamble. So that's going to be it on expected value. We'll go ahead and leave the lecture there and call it good.